The title of my presentation is Analysis of a Numerical Model for a Fractional Generalized Fermi-Pasta-Ulam-Tsingo Equation. My name is Jorge Macias Diaz, and I'm coming from the University of Aguascalientes in Mexico. This is the schedule of my presentation, so I'm going to talk about some preliminaries firstly. Then I'm going to give the numerical method to solve the system I am interested in. I'm going to derive some numerical properties, and finally I'm going to produce some simulation. Okay. The motivation of this work are the alpha and beta Fermi-Pasta-Ulam-Tsingo chains, which are these systems of ordinary differential equations. This system is the alpha Fermi-Pasta-Ulam-Tsingo chain for n between 1 and n, and this is the beta Fermi-Pasta-Ulam-Tsingo chain. Okay, as you can see, these are systems of anharmonic oscillators, and they are very interesting because they exhibit many nonlinear phenomena, including chaos, equipartition, recurrence, supertransmission, and bistability. They're difficult to be studied from the analytical point of view. So what sometimes is done is people take the continuous limit of this systems and they obtain a single partial differential equation describing each of those systems. The partial differential equation is going to assume this form. The purpose of this work is to extend this partial differential equation to the fractional case scenario. To that end, we are going to fix a spatial domain A comma B, a space-time domain, which is going to be A comma B cross 0 comma T. We introduced the classical LQ spaces, the Q norm, and the inner product for L2 spaces. If U is a function and alpha is a real number, which is greater than 0, then we define the space fractional derivative of U of order alpha with respect to x in this way. So this definition, this operator is actually a linear operator, which extends the integer order derivatives that we know from classical calculus. There are various properties satisfied by these differential operators. For instance, one of them is this extension of the theorem of integration by parts, which is going to be very useful in our investigation. For the remainder of this work, we are going to let p be a natural number, alpha 1, so on, alpha p are going to be constants between 1 and 2. And the functions g are going to be all of them real functions. Our generalization of the classical Fermi-Pasta-Ulam-Tsingo continuous system is given by this single hyperbolic partial differential equation. Notice that when gamma is equal to 0, and when p is equal to 1 and alpha 1 is equal to 2, then we retrieve the partial differential equation that we had in this previous page. We impose also initial and boundary conditions. Okay. Associated with this system, there is a local energy density, which is given by this expression. And notice that this first term is actually the kinetic energy, and the other two terms are potential energy. The total energy at time t is actually given by the integral of the local energy density. So in other words, E is equal to the integral of H. And it is important to point out that various particular fractional models are obtained when gamma is equal to when gamma, p, g, and g1 take on specific forms. For instance, we can obtain the classical sine-Gordon equation, the nonlinear Klein-Gordon equation, the double sine-Gordon equation, the classical Fermi-Pasta-Ulam-Tsingo equation, and the elastic string equation. If U satisfies the initial boundary value problem, then the derivative of energy with respect to time is given by this expression. In other words, the energy is dissipative in the system. The way to prove this result is just by taking the derivatives in the expression of the energy. So we take the derivatives of those terms, we put them together, and then simplify, and we finally obtain this result. As a consequence, if the g's are non-negative functions, then the energy is going to be always non-negative. Moreover, using these properties, it can be established easily that these terms, this one here, and this one here, are all of them going to be bounded uniformly with respect to time. Okay, C is this constant, which depends only on the initial conditions. Okay, motivated by these results, what we'd like to do is we would like to provide a numerical method with as many properties as those satisfied by the numerical model, by the continuous model. Okay, to that end, we're going to fix a uniform partition of the interval a comma b. So the norm is going to be equal to h, and a uniform partition of the interval 0 to t, which is going to have norm equal to tau. Okay, we introduce the usual discrete inner product, the p norm, and the infinity norm. We recall some traditional difference operators, which are going to be these ones. And recall this definition introduced by Ortigueira some years ago. So suppose that f is a function, h is greater than 0, and alpha greater than -1. Then the fractional center difference of order alpha of f at the point x is given by this double series. The coefficients in this case are going to be given by this expression. Those coefficients satisfy some recurrence relation. G0 is greater than or equal to 0. All the remaining ones are symmetric and less than 0. And the double series of the coefficients converges to 0. Moreover, if f is sufficiently smooth, then this discrete operator approximates this continuous operator with quadratic order of consistency. Okay, motivated by that, by this theorem, we introduce this discrete operator. And recall that it has some interesting properties. Namely, we can say that this operator is self-adjoint and negative, which implies that minus that operator has a square root operator, which is actually this one here. Moreover, there are some bounds for those operators, and they are well known in the literature. We continue introducing some other nonlinear operators, which are also well known, like this one here. And thus, the finite difference scheme to solve the initial boundary value problem that motivated our discussion is given by this system of discrete equations with initial conditions and homogeneous Dirichlet boundary conditions. This numerical model is an explicit model, which implies that the existence and uniqueness of the numerical model is guaranteed. So that's no problem. And there is also a discrete energy density associated to our model, which is given by this expression. The total discrete energy density at time Tn is given by this formula, which is just the integral of the discrete energy over the discrete space. We need some formulas, some expressions, in order to establish the property of dissipation of energy, which is stated next. Suppose that U is a solution of the finite difference scheme, then the discrete rate of change of energy is given by this expression. Notice that this is negative, less than or equal to 0. Thus, the energy dissipates in the system. The proof is relatively simple. We just need to use the equations in the previous lemma. Let's go over the numerical properties now. So we are going to introduce this continuous operator and this discrete operator. This is just the expression of the differential model. This is the finite difference model. Suppose that U is sufficiently smooth solution function. Suppose that the functions G are also sufficiently regular. Then there are constants C and C1 in such a way that the difference between this continuous operator and this discrete operator is bounded by this term. In similar fashion, the continuous Hamiltonian and the discrete Hamiltonian is bounded by this expression. In particular, we can say that the finite difference scheme is a second order consistent discretization of the continuous model. Okay. In order to establish the stability and the convergence of the scheme, we are going to require some lemma. So this is a lemma taken from the literature, which helps us to bound some terms which appear in stability and convergence. This is another lemma. So this is also helpful to bound terms. Okay. I'm going to skip the proof for reasons of time. We also need a discrete form of Grunwald's inequality. So this is a discrete form of Grunwald's inequality that we are going to require. And this is our theorem on stability. Suppose that the functions g are sufficiently smooth. And suppose that we have two sets of initial conditions, phi v and phi w, and that their solutions are respectively v and w. Let epsilon be the difference between v and w, and define these constants omega k, which depends on the approximation at time around time k, and rho, which depends on the initial approximations. Then there exists a constant c, which is independent of tau, with the property of omega k is bounded by this constant. It's obvious from here that stability of the numerical method can be established readily. For convergence, we need to assume that the solution u of the initial boundary value problem is sufficiently regular and that the functions g are also smooth, sufficiently smooth. Then the numerical solution converges to the exact solution with convergence rate equal to 2 in both space and time. Now about the proof, so we let epsilon be the difference between the exact solution and the numerical solution. We establish firstly that this difference is satisfies this discrete model, where R is actually the local truncation error, which, by the way, according to consistency, satisfies this property for some constant C0, which is independent of tau. Okay, we follow the energy method. So following the energy method, we obtain that this quantity is bounded subsequently by these expressions. These expressions result from the previous lemmas. We continue bounding, and at some point we reach a form of the discrete Grunwald's inequality. So here omega k is given in this form, rk is given in this form. And from here, we apply the Payne-Hughes lemma, which is the discrete Grunwald's inequality. And using Grunwald's inequality, we can establish readily that this happens. Whence it follows that the errors are bounded by a constant, which only depends on tau, times tau squared plus h squared. So convergence has been established then. We go now to some simulations. Let's consider firstly the case of the undamped elastic string. So in each of these graphs, we have time and we have x, and we have different values of alpha equal to 2, alpha equal to 1.6, and alpha equal to 1.2. First row are solutions, second row are Hamiltonians. That was for illustration purposes. Here we show the dynamics of the energy with respect to time. So for different values of alpha equal to 2, 1.8, 1.6, 1.4, 1.2, 1.1, and different values of gamma therein. So gamma equal to 0, so on. Notice that when gamma is equal to 0, the energy is approximately conserved, as expected. So when gamma is not equal to 0, then the energy is dissipated, in agreement with the theoretical results. We consider now the case of the undamped Fermi-Pascal undamped single chain for different values of alpha. Okay. for solutions, for Hamiltonians, and then we consider the dynamics of the energy. Okay. Again, when gamma is equal to 0, the energy is conserved. When gamma is not equal to 0, the energy is dissipated, in agreement with the qualitative results. We also performed a numerical analysis of the convergence of the scheme. We found out that in time, the convergence is quadratic, approximately quadratic, and in space, also quadratic, quadratic. To conclude this talk, a fractional extension of the Fermi-Pasta-Ulam-Tsinghua model was proposed. A conserved energy functional was derived. A conservative scheme was proposed and fully analyzed. This is the first work in which these tasks have been achieved, and it's easy to extend the study to multiple dimensions. I'd like to thank finally the organization of this event and the National Council of Science and Technology of Mexico for its support. And this is information to contact me. Thank you all.